Good morning. I am going to start part 2 of section 4.3. We're going to see what the second derivative tells us about the graph. By the way, I hope everybody's doing okay. And maybe I am getting a little bit better at this. Let me know what you think. Okay, so the second derivative is going to tell us about the concavity of a graph. And I've drawn you two pictures, one in which the graph is concave upward on an interval, so it looks like a bowl that would hold water. And then concave down is the upside down bowl that would spill the water. I'm going to draw some tangent lines to the graph at each of these points. For the concave upward portion, we've got some negative slope. Here it looks like maybe the slope becomes 0 and then positive. So I'm going to label this f prime is negative to f prime is positive. So as you can see, it goes from a negative number to a positive number. On an interval in which the graph is concave upward, that will happen. F prime will increase in value. On a concave downward interval, f prime will start out as a positive number and then change to a negative number. So f prime is going to decrease in value. If I want to see where a function f increases or decreases, I analyze the sign of its derivative. So if I want to see where f prime increases or decreases in value, I'm going to analyze the sign of its derivative. F prime will be increasing on intervals in which f double prime is positive, and f prime will decrease on an interval on which f double prime is negative. That's how we're going to tell whether a graph is concave upward or downward. A graph will be concave upward on intervals in which the derivative is positive, and it will be concave downward on intervals in which the second derivative is negative. Where the second derivative changes sign from positive to negative or negative to positive will be called a point of inflection. That's going to be a place where the second derivative is 0, or in some cases, where the second derivative does not exist. So when we go about our graphing strategy, after we do all that business that we did with the first derivative, find critical numbers, check the sign of f prime, identify where the graph is increasing, decreasing, has relative max and mins, then we'll do it again, but with the second derivative. Take the second derivative and set it equal to 0. Use a number line to see where the second derivative changes sign. And then our decision will be wherever the second derivative is negative, it will be concave downward. And wherever the second derivative is positive, it will be concave upward. So it just adds a whole nother layer to our graphing strategy. So here I've got an example. I've taken a fourth degree polynomial, and I want to use the first derivative to get the intervals on which this thing is increasing, decreasing, and find the max and mins. Then we're going to use the second derivative to find the intervals in which the graph is concave up and concave down. Then we'll sketch a graph. So let's do all the stuff with the first derivative. So first we take f prime. In this case, it's 16x minus 8x to the third power. We're going to set that equal to 0, so let's go ahead and factor it. I think I have a common factor of 4x, and that leaves me a 4 here minus 2x squared. I guess I could have taken out 8. That was kind of stupid. Let's try it again. Let's take out the 8. Got to get my coffee to kick in so I don't make those mistakes. So I'm pulling out an 8x, and that leaves me a 2 minus x squared. Now let's set each factor equal to 0. This factor is 0 when x is 0. And this factor is 0 when x squared is equal to 2, and so that's when x is equal to plus or minus the square root of 2. So I have 3 critical numbers. This is important. If you can't factor something and you've got an x squared, make sure you get both square roots. Now we're going to look at the change in sign of f prime. So let's put our critical numbers in order. Negative square root of 2, 0, and the square root of 2. And we're analyzing the sign of f prime. And that's going to tell us the direction of f. Okay, so I'm plugging numbers into here. Square root of 2 is about 1.4, so if I put in maybe a negative 3, my first factor, 8 times negative 3 is negative. 2 times negative 3 squared is also negative. A negative times a negative is positive. In here, in the next interval, I can choose negative 1 as my test point. 8 times negative 1 is negative. 2 minus negative 1 squared is positive, so in there my derivative is negative. In my next interval, between 0 and 2, I'll pick 1 as my test point. Both factors are positive there. And beyond square root of 2, I'll put 3 as my test point. 3 times 8 is positive, but 2 minus 3 squared is negative, so my overall product is negative. And the direction of f is that it rises where it's positive and falls where it's negative. Up, down is the way it looks. So we write it like this, that it's increasing to the left of negative square root of 2, and then again between 0 and the positive square root of 2. The graph is decreasing between negative root 2 and 0, and then again beyond positive square root of 2. Which gives us a relative max at both of the square roots, and a relative min at 0. So that takes care of everything with the first derivative. Now let's take the second derivative. So we're on our third step. F double prime is going to be 16 minus 24x squared. We're going to set that equal to 0. So I'll have 16 is equal to 24x squared. 16 divided by 24, is that 2/3? And so take 2 square roots here. X is plus and minus the square root of 2/3. Those are our 2 inflection points. So let's go over here and check the sign of f double prime about those 2 inflection points. So 2/3 is smaller than 1, so the square root of 2/3 is in the neighborhood of 1, right? But not quite as big as the square root of 1. So in here, as my test point, I can use -1. When I plug -1 back into my derivative, my second derivative is 16 minus 24x squared. So if I put in a -1 or even a +1 and square it, I get a 1. 16 minus 24 is going to be negative. So both of those intervals will be negative. In between, I can use 0 as my test point, which shows me my second derivative is positive. So the concavity of f is that it's concave downward on the 2 intervals in which the sign of the second derivative is negative, and concave upward in between here. So we'll write that as concave down to the left of negative square root of 2/3, and then again to the right of the square root of 2/3. And it's concave upward between those two radicals. Now I'm not going to worry about plotting those points. I'll just kind of fake those. When we go to sketch the graph of this thing, let's look at the y values at the critical numbers, plot those, and then we'll squeeze in the inflection points after we have the graph drawn. So I'm going to go back up to my function, 8x squared minus 2x to the 4th. And at plus and minus square root of 2, I can do them both together since those are even powers. The square root of 2 squared is 2. 8 times 2 is 16. The square root of 2 squared is 2, so when you square that you get 4. 2 times 4 is 8. So at the square root of 2, my y values are 8. And then, of course, at 0, I get 0. Let's get a graph that shows those points. Probably should make that prettier, but too bad. All right, so it's square root of 2 and negative square root of 2. Let's go ahead and make our scale to there. We're up here at 8. Let's label them. And then we have 0, 0. Now we look at the direction of the derivative. So let's go back up here. It's got to rise, fall, rise, fall. So it's going to kind of look like an M. Let me do that in green. We're going to rise. And we have a horizontal tangent line, fall, horizontal tangent line, rise, horizontal tangent line, fall. Then somewhere in here, this is somewhere in between 1 and negative 1, we've got an inflection point. So let's just put our inflection points right there. We've got that it's concave downward here, concave upward between the two inflection points, and concave downward beyond. And now let's follow the arrows and draw a graph. Since it's a polynomial, we can make things nice and smooth. So it looks like to me it's going to be something shaped like an M. Up, hit the horizontal tangent line, come down, change concavity. Now we're concave up. Now we're going back to concave down. How about it? Looks good, doesn't it? I'm going to stop my music. Why is it still playing?